Hi, my name is Aaron Abraham and I will be presenting about electric vehicles today. So first we'll look at what classifies a car as an electric vehicle. Traditionally we have conventional internal combustion vehicles which are powered by gasoline. They are cheap to buy, but the price of gasoline is rising. Electric vehicles are powered by an electric motor only. They are more expensive, but they have much lower energy costs. And then we have hybrid vehicles. These use both a gas engine and an electric motor. They are less expensive but have higher fuel costs compared to pure electric cars. So why do we need electric cars? The supply of gasoline is limited and the price of gas is rising steadily. Pollution from burning fossil fuels is also causing a major problem like global warming. Most renewable sources of energy can produce electricity like solar cells and hydroelectric dams. There is already a good infrastructure for electricity distribution present in most homes, so electric cars would be a convenient way to use renewable sources of energy. Electric cars can also give us energy independence from the few countries that have oil. Now we'll look at the parts of an electric car. The electric motor is the component which provides propulsion to move the car, and the batteries are what stores the energy so that the car can be moved. And the controller provides power to the motor based on the throttle position. Different forms of energy storage that we will look at include lead-acid batteries, nickel metal hydride batteries, lithium-ion batteries, and hydrogen fuel cells. Lead-acid batteries are one of the oldest forms of rechargeable batteries that we use today. They're present in conventional and hybrid cars for starting the engine and running accessories. They're also present in electric vehicles to run accessories at 12 volts. They are cheap to buy but have very low energy density compared to other battery technologies. So now let's look at what happens inside a lead-acid battery. Lead dioxide is used as the cathode or positive electrode, and lead is the anode or the negative electrode as shown in the diagram. The electrolyte that's used is usually sulfuric acid, and when a battery is discharging, the equations at the bottom run from left to right. So the equation on the right side shows what happens at the negative electrode, and it shows that lead reacts with sulfate ions to produce 2 electrons, and at the positive electrode, 2 electrons are absorbed when lead dioxide reacts with sulfate ions. So you can see there's a flow of electrons through the wire from the negative to the positive electrode. So this electricity can be used to run a load such as electric motor, and as you can see in the diagram, current is labeled from the positive to negative because, as you know, the flow of current is opposite the flow of electrons. When you're charging a lead-acid battery, you have to apply a voltage across the terminals. This causes the reactions to run backwards. So both the reactions at the bottom will be running from the right to left side. And as you can see, on the positive electrode, the lead sulfate reacts with water to create 2 electrons. And on the negative electrode, lead sulfate absorbs 2 electrons to break up into lead. The electrodes then go back to their original states of lead and lead dioxide, and hence you have a fully charged battery. Nickel metal hydride batteries work on the same basic principles, but they have a higher energy density but a higher cost as well. They're used in most hybrids like the Toyota Prius. The anode is usually a metal hydride and the cathode is a nickel oxyhydroxide. The electrolyte is usually potassium hydroxide. The metal M is not an element and is actually a rare earth intermetallic compound. So charging occurs when both the reactions at the bottom run from the left side to the right side. And again, as you can see, the anode releases an electron and the cathode absorbs an electron. Now we'll look at lithium-ion batteries. They have a much higher energy density and cost, but they're much more lightweight comparatively, and hence they're used in most new electric vehicles like the Nissan Leaf and Chevrolet Volt. The difference between this battery and the others is that the anode is a lithium carbide and the cathode is a lithium cobalt dioxide. And the electrolyte that's usually used is a lithium salt. And as you can see, there are similar equations at the bottom to show how what occurs in a lithium-ion battery electrically. Now we'll compare the batteries that we have looked at. This table shows a comparison of the batteries at similar energy levels, and this shows that lead acid is the cheapest, with lithium-ion being the most expensive. But lithium-ion has the most energy density in terms of mass and size. Hence, the weight of such the equivalent lithium-ion battery is a lot lower than similar lead acid or nickel metal hydride. Hence, it is used in most pure electric vehicles. But because of the high cost, nickel metal hydride is still used in a few hybrid vehicles. Now we'll look at hydrogen fuel cells. Compressed hydrogen gas is stored in a tank, and the fuel cell can then convert it to electricity for the electric motor. This has the advantage of no long recharge times compared to recharging a battery. The most promising type of hydrogen fuel cell is the polymer exchange membrane. In this type of design, you have hydrogen coming in from the tank, and when it reaches the catalyst, it breaks up into positive hydrogen ions and electrons. The proton exchange membrane only allows positive ions to pass through it, hence the electrons are forced to pass through the electrical circuit where it can power a load. When the electrons come back to the catalyst on the right side, it meets with the hydrogen that have passed through the membrane and oxygen, which is split up into ions because of the catalyst. They then form water, and this is released as the exhaust from the fuel cell. So as you can see, hydrogen and oxygen are combined to create electricity, and the only byproduct is water in the form of vapor. Hydrogen is normally produced through the electrolysis of water as a byproduct of some industrial processes or steam reforming of natural gas. These methods do release greenhouse gases unless the electricity used in the electrolysis is renewable. Now we will look at controllers. Controllers provide the required voltage level to the motor from the battery. They can then control how much output speed is given from the motor according to what input from the user. The controller in an AC motor also converts DC voltage from the battery to an AC voltage. Now we will look at the common electric motors that are usually used in an electric car. Electric motors are usually AC or DC. The most common DC motor is a DC brushless motor, and AC induction motors and permanent magnet synchronous motors are used. So the DC brushless motor, as you can see in the figure, has both a stator and a rotor. And the stator consists of electromagnets, which are in the form of coil windings along the arm. And the rotor has permanent magnets, and in this picture there are 4 poles, north, south, north, south. So when a switched DC input is applied to the windings in the stator, it creates a pseudo-rotating magnetic field. The poles of the permanent magnet are attracted to the opposite poles of the electromagnet and follow it, hence causing the rotor to rotate. This rotation is then provided as the output of the motor. So why do we need electric cars? The supply of gasoline is limited, and the price of gas is rising steadily. Pollution from burning fossil fuels is also causing a major problem like global warming. Most renewable sources of energy can produce electricity like solar cells and hydroelectric dams. The stator of an AC induction motor is shown below. This consists of wires which are wound in groups to create a set of electromagnets. When an AC supply is attached to these wires, it creates a rotating magnetic field in the stator. The rotor of an AC induction motor is shown below. This is of the common squirrel cage type. An electromagnet is induced in the rotor from the stator current. Torque is created by the interaction of the magnetic fields from both the stator and the rotor. A permanent magnet synchronous motor works similar to an induction motor, but it uses permanent magnets instead of needing electromagnets induced on the rotor. This design has more torque, but has less temperature resistance, and rare earth metals are needed. When the permanent magnets are added, it makes it a synchronous motor, hence making controlling the output speed a lot easier than in induction motors. Thank you, and I hope you enjoyed the presentation.